Hi everybody, welcome to Module 5. In this one we're going to be looking at geological hazards. And for this module there's readings on Canvas on kind of basic geology, earthquakes, tsunamis, and volcanoes. And there is a decent amount of information for this module. And my apologies, I know that on one of the PDFs I think some stuff got cut off a little bit, but I think for the most part things are in pretty good shape. Unfortunately, after I rather than assigning the entire textbook for this class for the natural hazards book that some of these chapters came out of, I thought I'd just scan them in, and I think most of them worked okay, but it's my apologies if there's little places here and there where it's cut off. That shouldn't happen really in any of the other readings that we have coming up. Okay, speaking of things that are coming up after this, in the one of the assignments coming up is going to be the annotated bibliography assignment, which is due kind of after this module, and then we'll get into atmospheric hazards for the module after that. And just as a reminder, the annotated bibliography assignment, basically you're going to be doing research on a topic that associated with apocalypse or catastrophe, and finding sources, and some of those have to be scholarly sources, and I'm going to post something online in the under files kind of describing just what those mean and kind of what's expected for that assignment. So you'll see some stuff on that coming up in some announcements. There's another video for this section on the geology of Hawaii. The reason I focus on Hawaii is a couple reasons. In 2018, there's so much volcanic kind of eruptions going on in Hawaii that it seemed like a very kind of, because it's a current or contemporary event, to kind of take a look at that particular geologic site because of all the hazards there. And also because there's so many different kinds of hazards there between volcanoes and earthquakes and erosion and all sorts of other things. And I think this video gives a good idea of kind of what's going on with that. And so the kind of the academic content, if you will, for this, or the scientific content, is this lecture video as well as the Hawaii geology video, and then we also have a movie like we do with most modules, which is called Super-volcano, which is sort of a fictionalized account of like what would happen if the Yellowstone volcano went off in fully. And so that is located at that URL there. And one of the reasons why super-volcanoes are considered to be an apocalyptic event, and I apologize, this got a little cut off here, but if you look at the amount of stuff that comes out of a volcano at any given time, some of the volcanoes that are fairly kind of famous eruptions, like Mount St. Helens, is pretty small. Other eruptions in Mexico are pretty small. Even some of the largest volcanic eruptions that have gone on during recorded history, such as Tambora and Krakatoa in Indonesia, they put out, a fair amount of stuff into the atmosphere. But if you actually go back to things like Toba, which was a supervolcano, this was about 2,800 times as much stuff came out of this volcano as came out of like Mount St. Helens or some of the more well-known, recent eruptions. And this was something that happened about 75,000 years ago, and it's something that, by all reports, this is where humans as a species could have become extinct, because there's a bottleneck in terms of how many human beings actually made it through that time period. Historically, 75,000 years ago, it was such a large eruption it really almost led to the extinction of human beings. And so supervolcanoes, they do happen. They will happen again at some point, and they are tremendously large events, which are much bigger than normal volcanoes. And we'll get to that as I talk about volcanoes here in this section. Oh, there's my bigger picture of this, even though it's a little bit fuzzy. My apologies. But this is showing how much more stuff, ejecta, that came out of the Toba supervolcano 75,000 years ago compared to most of the more recent contemporary eruptions. Okay, so there's a lot of material here in this module, and the way I'm going to arrange this for the video lectures, I'm not going to go through every single piece of material that's in the reading, but I'm going to really focus on 4 big points. Now, there is on the PowerPoint that's going to be posted, it'll have the stuff that I'm going through on this video lecture, but then there's going to be supplemental slides on that PowerPoint. And what I recommend is that people just kind of go through it, particularly looking at how things match up with the the study guide for the first exam, because there is some material that you'll need to know that's from the readings and from these later slides that I'm just not going to get to in the video lecture, because otherwise, honestly, this video lecture would be like 2 hours long, and you probably don't want to watch that. So I am just going to kind of focus on 4 big major points, and it's still going to take a little bit of time to go through here. All right, so starting with kind of basic geology in terms of what I want folks to know. In a class like this, when we're looking really at hazards and things that cause catastrophes, the part of the Earth that we're most concerned with is the crust, which is right up here at the very tippy top, right, of the Earth's structure. We have, you know, kind of an inner core, an outer core, a mantle, and then the crust here, this area here is actually kind of showing it blown up a little bit. The crust, if you look at it in terms of its actual scale compared to the rest of the planet, is sort of kind of like the skin of an apple on an apple. And so that's really the part of the Earth's structure that we're going to be really concerned with in this course. And it's just kind of important to note that it really is this very tiny kind of area of the Earth. But that's where we are, and that's where all kind of the action is. And this is a part of the Earth that's actually quite dynamic there at the crust. So the crust is what's kind of on the very top of this whole lithosphere of the whole Earth. And there are 2 major types of crust, and it's important to kind of understand these because, as we'll see when we're looking at earthquakes and volcanoes, it kind of matters whether we have what's called continental crust or oceanic crust. There are kinds of crust that are predominantly under the oceans, like on the ocean floor, and then continents are actually a little, their rock type is a little different and it has a little more aluminum, it's a little bit lighter. But both crusts are kind of mostly silica based, but there's a little difference in terms of their densities. And so continents sort of sit on top of this oceanic crust because it's a little bit less dense. And one of the things about this too is that oceanic crust, everywhere you go in the whole world, is relatively young geologically. There's nowhere that you can really find seafloor that's more than 200 million years old. It's all kind of less than that. Continental crust, however, can be up to several billions years old. And a lot of that has to do with the fact that the oceanic crust is sort of being recycled and kind of put into the Earth and remelted and then reformed as it kind of comes out. And I'll talk a little bit about that. But the continents sort of sit on top of those oceanic crusts as they move around. And we'll talk about that here. Now, the way we know about some of this internal structure of the Earth and the different kinds of crust and all that, you know, as a species, we actually haven't drilled down like really all that far into the Earth. The way we actually know about some of the structures of the Earth's, about the Earth's structure is really from the study of earthquake waves, because we can see the way these earthquake waves kind of go through the whole planet. And there are certain kinds of waves that can go through liquid, some that can't, and also ones that move. The earthquake waves move differently depending on the density of what they're moving through. And so that's how we're able to really kind of map out this kind of deep geology of the planet. And we'll talk a little bit about that when we get into earthquakes, but I kind of wanted to make note that this is basically how we know what the Earth's structure is internally. It's not from drilling down in there. It's by the fact that there are certain earthquake waves called S waves that cannot go through liquid. And so if there's say an earthquake here and you have all these seismometers that are reading the earthquake waves, you can see where the S waves make it through and you can see where they don't. And then there's something called P waves caused by earthquakes that do go through liquid, and so you can kind of tell what parts of the Earth are liquid, which ones aren't, and also by the way they kind of bend and the amount of time it takes to get through, you can tell things about density. So that's kind of where some of this information comes from. So one of the things that really drives a lot of the processes that are, really cause disasters, things like tsunamis, earthquakes, volcanoes, has to do with the fact that the Earth's crust is moving around. And this is basically the theory of plate tectonics, which is the idea that the Earth's crust is broken into several pieces and they all kind of move and kind of bump up against each other. And so this is a basic map of how plates move around the Earth. And so you've got some major plates like the Eurasian plate, the North American plate, the Pacific plate, and the South American plate. And again, the important thing to recognize here is that the plate boundaries, for the most part, tend to be in the ocean. Not all the time, but for a lot of them. And where those plate boundaries are, the difference between the plates is that the plates are all oceanic crust, but you have these continents sort of riding on top of them. And so the continents are sort of embedded in these oceanic crusts as they move. And there's a few different kinds of boundaries they're showing here. The blue boundaries are what are called divergent boundaries, where the continents are essentially moving apart from each other. And then the arrows are where they're moving towards each other. And so you can see these red arrows like right here. The mid-Atlantic is a place where the continents are kind of spreading apart from each other. And then there are areas where they're colliding, such as where India and the Indo-Australian plate is smashing into the Eurasian plate. That's a place where they're coming together. Also, there are places where the Pacific plate is diving underneath the Eurasian plate here. Or where the Pacific plate is diving under the North American plate. And you get these different kinds of boundaries. And I'll discuss, kind of why these boundaries matter in terms of the different kinds of disasters that we see. Because the way that geologists kind of discovered that these boundaries exist was actually by mapping out volcanoes and earthquakes. That's how we kind of discovered where these plate boundaries are, because earthquakes and volcanoes are mostly associated with plate boundaries. So, for instance, if we look and we take a map of recent earthquakes and volcanic eruptions, we see a definite pattern, right? There are some places that have very, very few earthquakes, like actually where we are here. They occur, but not very much. Whereas if you go around the Pacific Rim, you have a ton of them. If you go in the mid-Atlantic ridge here, you have a ton of them. And also volcanoes tend to happen in certain areas too, and those also tend to be where these plate boundaries occur. So, and the reason why these plates move around and kind of bump into each other and all this has to do with the fact that inside the Earth there is different parts of the Earth are being heated are hot and are differentially hot, I guess is a good way of putting it. The temperature varies in different parts of the interior of the Earth, and this sets up what are called convection cells, where places that are warmer tend to the energy there kind of rises and moves the Earth's material upward, and then where it's colder, it tends to kind of sink back down. The same way that when you're boiling water on your stove, it heats up the water right over the burner. That hot water rises up and creates these convection cells. And so essentially the same type of thing is going on over miles and hundreds of miles in the Earth's under the Earth's surface, and that's what's kind of moving these plates around on top. It's almost like if you had like things moving around on top of the water, like if you're saying if you were making macaroni and cheese and everything's boiling, the macaroni and stuff's kind of moving around with the water currents. That's to some degree kind of what's going on the Earth, except obviously it's happening much slower. Okay. So a few things about kind of this idea of plate tectonics is that you're adding new crust at the areas where we have these spreading zones. And then the crust is getting destroyed where it's kind of sinking down into the Earth. But the Earth, of course, remains a constant size, and so you're just kind of recycling this material, bringing it to the surface, and then kind of having it go back down. And so I want to go to this picture here. This kind of shows this as a diagram, whereas if you go to where you have the spreading zones, which are typically in the middle of oceans, like in the middle of the Atlantic Ocean, there is one on land. The Rift Valley of East Africa is a spreading zone that's on land, but most of them are in the ocean. And what happens is that this is a place where new crust is being formed, and you're getting volcanism that's creating this new crust, and it's pushing these plates apart from each other. And then where this plate here, let's just say for argument's sake, this is the Pacific plate and this is the North American plate, and we're looking at, say, the area around Oregon and Washington. It's a little complicated there. There's another small plate called the Juan de Fuca, but for our purposes here, we'll pretend that these are two major plates kind of coming together here. What happens is that as they bump into each other, one of the plates is denser than the other. And so what happens is one of them, if they're coming together, they hit, one of them starts to dive underneath the other one like this. And so what's going on here is that it's showing you that this plate is moving this way, this plate's moving that way, and this one dives under. And this is what's called a subduction subduction zone or subduction boundary. And what happens at these subduction zones is that these plates kind of stick to each other sometimes, and then this builds up energy, and then when they release, that creates really large earthquakes. So some of the largest earthquakes in the world are on subduction zones. The other thing that happens is that as the plate dives underneath and it carries water and other things with it, it comes down here and it starts to melt. And usually about 100 miles or so inland from where this plates come together, you get melting, and the magma bubbles up, and you create a string of mountains just off, away from this subduction zone. So, for instance, in the Pacific Northwest of the United States, you have a plate that's diving underneath the North American plate. It melts, and then you have this long string of mountains like Mount St. Helens and Mount Hood and Mount Rainier in the what's called the Cascade Range. And those are all volcanoes, and they're all in this kind of line that are about 100 miles away from where that subduction zone is. You get the same thing in Japan and in Indonesia and other areas where you also have a subduction zone, and then you get this line of volcanoes. Okay, so this, and subduction zones are some of the most, some of the areas, again, of really big earthquake activity and volcanism, and this is kind of that first one that we were just looking at here. But sometimes what happens is this happens not with a continent, but just out in the middle of the ocean, in which case you end up with a line of islands, things like Japan, as well as the Mariana Islands and a few others. But one of the things that can happen too is that eventually, like what you see with India and the rest of Asia, is that the two plates have come together. There's no ocean anymore. It's just two continents. And you don't really get volcanism, but you do get earthquakes and you get crumpling, and this creates large mountain ranges. Like, for instance, the Himalayas are created by when you have two continents essentially coming into each other like that. Okay, so the other kind of area of the Earth that we have to think about besides just plate boundaries is also what are called hotspots. And hotspots tend to actually be in the middle of plates, not always, but to some degree. And so, for instance, there's an example of one that's on a plate boundary is like Iceland. Iceland is a hotspot that's also on a spreading zone. But there are places like Hawaii, which are actually smack dab in the middle of the Pacific plate. They're not near any kind of plate boundary at all, where you get a lot of volcanism. And also Yellowstone is another hotspot. And basically what happens there is, instead of it being this place where plates are coming together, you just get a part of the Earth's geology that's just very, very hot and has a lot of rising magma in one kind of point or location. And what happens is that as the plate moves over that hot spot, it creates all of these volcanoes, usually in a line. And so let me show kind of a video or a picture of this. So for instance, this is the Hawaiian hotspot. You have this hot spot where the stuff's volcanic material is coming up, and it's just, kind of think of it almost like a fountain kind of coming straight up. And what's happened is that the Pacific plate has moved over time. And so the older islands, and you'll see this in that video on Hawaii and its geology, the older islands used to be over the hot spot, but then the plate has moved. The hot spot stayed where it is, and as the plate moves, it creates an island here, and then an island here, and then an island here, and so on. And so you can see, like, for instance, the Hawaii island is being remade even as we speak today. The Kilauea has been erupting continuously since 1983. But as you go down the island chain, the islands get older and older. So Maui is about 1 million years old, Molokai about 1.3, Oahu 2 to 3 million years old, Kauai, etc. And if you remember, Kauai used to be over here, over this hot spot, but the plate has moved. How long has this been going on? A long, long time. Over 80 million years. You can actually, if these are the main islands of Hawaii, but if you look at what's underwater, you actually still have this chain of mountains, mostly underwater, that goes all the way out to Midway, which is slightly above the water. But then you also have what are called seamounts, these other volcanoes and mountains that are submerged. But the chain actually goes all the way to the Aleutian Islands out here. And so this is a process that's been going on for a very long time. But again, that's something that you don't see. Most volcanoes are not hotspots. Most of them are kind of these subduction zone type of things or spreading zone volcanoes. Um, let's see here. There's one other thing I wanted to show. Well, I'll get to it here in a second. Let me when we continue talking about the volcanoes here, there's a few different things about the types of volcanoes. Is that how dangerous they are depends a little bit on what's called their silica content. And so different kinds of lava, or what they refer to as magma, magma is the word they use when it's underneath the surface, and then lava is what we call it when it's kind of flowing out on the surface. And how much silica you have in the lava changes its viscosity, and viscosity has to do with sort of how well it flows. So like think of something like honey or toothpaste. Like these are things that are more viscous than water, right? And so lava is the same way. Some lava is very runny and some is very viscous and thick. And so basically there are three major lava types. Basalt, which is a very kind of low viscosity, it's very runny type of lava. The kinds of lava you see flowing in a place like Hawaii is basalt lava. It doesn't really explode out a whole lot. It just kind of flows, and maybe it comes out in a fountain, but then it just kind of runs down, the slopes. Andesite, on the other hand, has more silica and is more explosive. So like Mount St. Helens would be an example of an andesite kind of volcano. When it erupts, it tends to, because the lava is so much thicker, it has a higher gas content, it just kind of explodes out. And then one of the more explosive types is called rhyolite, which is a little more rare, but there are definitely examples of it. But it is even more viscous, and again, it is much more explosive when it erupts. So the basalt type of volcanoes create things like shield volcanoes, this is in Hawaii, and basically because it's just one lava flow that kind of comes up over another, and it's very fluid, and so it just kind of comes down and creates this type of a shape of a mountain called a shield. Whereas composite volcanoes are volcanoes that are made out of andesite. And so because the lava and stuff is a little thicker, it doesn't just kind of run out, it kind of explodes and then creates these falling debris and stuff. It makes these type of volcanoes that are more kind of the way we think of probably the shape of most volcanoes, like Mount Shasta or Mount Rainier, Mount Fuji, Mount St. Helens. Those are all composite volcanoes. And then the most explosive kind of volcano, the rhyolite types, are what are sometimes referred to as volcanic domes. And so these are a little more rare, but like there are some like in California and other areas that are made from very, very thick lavas. And therefore the eruptions are very explosive. Now the other kind of volcanic eruption, which is rare but very, very destructive when it happens, and it's also kind of the subject of the video super-volcano that you're going to watch, are what's referred to as caldera eruptions. When caldera eruptions go off, they do damage over very, very wide areas. They put a lot of stuff into the atmosphere, which has all sorts of climate effects and kills things for a very long way. And so basically a caldera eruption has to do with when you have an area with a lot of different volcanism, and you have a large reservoir of magma, which usually might just kind of come up and erupt into small volcanoes. What happens essentially is you get a collapse of the entire area where there's a lava or a magma chamber underneath, and it collapses in and the whole thing just sort of explodes out. And they explain this a little bit in the Super-volcano movie. And so, sorry this is blurry, but this is showing the hot spot that is Yellowstone, and the Yellowstone caldera chain. And so there have been this series of eruptions, and just like with Hawaii, Yellowstone is a hot spot that's staying in one place, but the North American plate is moving over it. And so the whole Snake River Valley of Idaho are these older, like if you go, Yellowstone's right here. This is where the volcanism is kind of at now, and you can go you can go down to the southwest, and they get older and older caldera eruptions that happened and kind of blew out these huge areas. And when the next one happens up here, That's what the movie is kind of trying to get into, is like, how damaging is that going to be when that kind of caldera eruption happens, because it'll be very, very damaging. This is just a little better picture of that, showing where Yellowstone is now, and then how many million years ago were these other calderas kind of created from these gigantic eruptions. And then you also have this area where there was a big flood of lava that kind of came out of these areas when they had some of these large eruptions. And Yellowstone is not the only place with a potential supervolcano with a large caldera eruption. Naples in Italy is in an area where the caldera around it is actually showing signs of waking up and becoming more active. And so there's some links there if anybody's kind of interested in following up on that. Okay, so been focusing a little bit on on volcanoes, but want to say a few things too, specifically about earthquakes. One of the big things with earthquakes, I've mentioned that most of the time these are associated with plate boundaries and have to do with kind of the sticking of the plates and the release of that energy. There are basically three major things that dictate just how bad the shaking is from an earthquake. And one of them is what's called the magnitude, which is just how much slippage occurs over what kind of a distance and how much energy is being released from that earthquake. The other thing that makes a difference for how much shaking you're going to experience is, as you would figure, is how close are you to that earthquake. The closer you are, the more it's going to shake. But the last one is also local soil and rock conditions. And so if you recall the video that we watched for the last module on the, just the quake from Port-au-Prince in Haiti, that wasn't a very big earthquake. The magnitude was only a 7.0, which is not really huge as far as earthquakes go. But the location of the epicenter was directly underneath Port-au-Prince. And the other thing is that the local soil and rock conditions were such that it kind of accentuated some of the shaking. And then, of course, the fact that they also had just really bad, poorly built structures and things like that is why the death toll was so high. All right. So one of the things about with earthquakes is that we can pinpoint them pretty precisely using seismometers, which are things that are measuring earth shaking. Because you have these different kinds of earthquake waves that come out from an earthquake and they travel at different speeds, we can actually figure out exactly where an earthquake happens fairly easily. And what I'm going to focus on here is these different kinds of earthquake waves, P waves and S waves, and the way that they travel out. So P waves in earthquakes they move very fast, but they actually are not all that damaging. A P wave is also called a compression wave, and essentially it's kind of the way the energy is being pushed out through the rock, almost like as if kind of like a spring, like where you are have this compression of the rock and then that's kind of moving through. And now, granted, when it hits, it jolts everything. And this moves through the rock very quickly. It can also move through liquids, and so it can move through parts of the earth, but like in the core, that's made of liquid, all of that. But the real damaging earthquake wave comes a little bit later, and it's what's referred to as S waves. S waves is where the ground is sort of not just being pressed this way, but it's moving up and down like this, or also kind of back and forth. It kind of has this kind of motion to it. It takes longer to get to you, but when it does this, and then you can imagine like a house with a house foundation and everything else all of a sudden starts going like this, and that's where stuff gets broken and things fall down. But the fact that these S waves move slower means that you have, in a sense, a little bit of warning. The P wave hits you, you get this jolt, and then the real kind of S waves come in a little bit later. And as mentioned, this is kind of how we know how the Earth's structure is based on when these P waves and S waves kind of move through it. And so this is actually a diagram showing the areas of kind of most intense shaking from the Northridge, California quake that happened a few decades ago. And one of the things that it's showing, it's a few things. One is that the shaking, the epicenter is what is known as the, kind of the spot on the Earth that the earthquake happened like directly under. And one thing that makes a difference too with how much shaking is how deep is the earthquake. Some earthquakes are much deeper in the earth, which don't shake as much, and then the ones closer to the surface cause more shaking. But this shows you the places that actually had the most shaking. And what's interesting is the epicenter, the place that's directly above where the earthquake happened, didn't have the worst shaking. The worst shaking was actually north of the earthquake's epicenter, And there's a few reasons for that. One is the soil conditions and things that existed over there, but also because the earthquake, the place where the fault kind of slipped had a kind of direction. So if the earthquake slipped this way, it put most of its energy that direction, and so it didn't come up necessarily straight up. It came off to the side in terms of the places with the most energy and then therefore the most shaking. So it's not always right next to the epicenter. And then in terms of the different types of rock that you're on and how much that affects it, if you're on very hard kind of volcanic rock, it doesn't shake very much. Sedimentary rock shakes a little more. Alluvium is kind of like a loose, like if you're in a place where you're in a river valley where it's kind of over time, there's been all this sediment kind of laid down, that shakes a little more. And then like silt, mud, or in areas that have been kind of reclaimed, like there's an area of San Francisco that after one of the major earthquakes, they took all the debris and dumped it basically into the bay, and then they kind of built on top of it, but it's very not as consolidated as rock. And then the next time there was a big earthquake, the things they had built on that area shook almost like a bowl of jello, and it really damaged a lot of the buildings. Mexico City is an example where that used to be basically a large lake and has been filled in, but it's kind of more like silt and mud, and so when it has earthquakes, it tends to shake really badly too. Okay, and then one more thing I wanted to hit here is tsunamis. That's a person right there who, as you can probably guess, did not live through the rest of the tsunami that was coming in. There have been some pretty major tsunami disasters in the world, and they have killed a large number of people. Some of the more recent ones, Japan, a tsunami, this is a magnitude 9.0 earthquake, killed about 20,000 people. But the Sumatran earthquake that happened in 2004 had created a tsunami that killed almost 250,000 people around the Indian Ocean. And one of the things, too, I should mention here in terms of earthquake hazard, and this is in the readings, but when we talk about magnitude, the scale of magnitude is not a linear scale. In other words, it's what's called a logarithmic scale. What it means is that for every number you go up, it actually increases the amount. They're talking about an increase in energy of 10 times. So for instance, if you have an earthquake that's a 6.0 earthquake, and then you have a 7.0 earthquake, a 7.0 earthquake is actually 10 times the size of a 6.0. An 8.0 earthquake is 10 times the size of a 7. So in other words, an 8.0 is 100 times bigger than a 6.0. And so when you see things on the news or whatever, or you talk about something like a 9.0, that means, like, remember the video we watched about Port-au-Prince, that was a 7.0 earthquake. The Japan quake was literally 100 times as powerful as the one that hit Port-au-Prince. And so some of these earthquakes that are like in the 9.0 range are gigantic earthquakes. And one of the things that happens when you have earthquakes in certain places is that it creates tsunamis. And basically how it works is that you have an area where there's some kind of subduction type of boundary, and then the earthquake happens, and when the energy is released, part of one of the plates basically moves upward. And if that happens at a fairly shallow depth and it's under the ocean, all the water above that plate gets pushed up all of a sudden, and water doesn't stay up, right? It's going to flow back down, and essentially that's what happens. So sorry, this is a little blurry, but the fault's here. You get this earthquake, part of the seabed rises, it creates this large bubble of water on the surface, and then it flows out in each direction. And then when it hits a landmass, it comes in as a tremendously powerful, very large wave and creates all sorts of death and destruction. But those are not the only way that tsunamis can be created. That's the most common way, is from earthquakes. But you can also cause them from just underwater landslides, or also landslides that are above water where the material falls into the water, creates a big splash, and that wave then comes, moves across the water surface. And so, and the thing with these landslide earthquakes is that they tend to create tsunamis really close by, and so they can be gigantic. Some of the largest tsunami waves, over 1,000 feet in Alaska, were caused by a landslide that kind of came into this one bay. And so, and you have almost no warning in terms of being able to get out of the way, because usually the tsunamis are so localized from this. But when you get an earthquake-caused tsunami, these waves actually travel over across the ocean in but take about the speed of, say, of a passenger jet. And so the earthquake happens here next to Indonesia, and this hit here in less than an hour and killed a lot of people who had very little warning other than they felt the earthquake shaking. But then there were people that never felt the earthquake in places like Sri Lanka, Thailand, India, where after 2 hours this large wave came and killed, as you can see, most of the people who died were in Indonesia. 167,000 people died. But then in India, you still had 16,000 people, 35,000 in Sri Lanka, 8,000 in Thailand. Even people in Somalia died 7 hours after the earthquake because this wave kind of went all the way across the entire ocean. And then one of the other things that can create tsunamis that are sometimes referred to as mega-tsunamis is when whole chunks of islands fall into the ocean. And the video you're going to watch about Hawaii talks about Molokai, which is this island here, and how it basically in one day, half of the island collapsed into the ocean. And this would have created a tsunami 1,000 feet tall at least, that would have, if it happened today, would have killed everybody pretty much in the entire Hawaiian island chain. And the thing that's kind of scary about that example is that there's evidence that this has actually happened almost 20 times around the whole island chain at some point geologically. And so when that happens, it creates these really, really large tsunamis. And so again, that video kind of talks about that, where the whole eastern flank of the volcano just fell into the, collapsed into the ocean and created this gigantic tsunami. And this is a big crack in the big island of Hawaii currently that's continues to separate at a fairly rapid, geologically speaking, a fairly rapid rate. It's this roughly 5,000 cubic mile chunk of island that's displacing towards the sea at about 4 inches per year, and the worry is that will it at some point just fall off and create a gigantic tsunami. In 1975, about a 37-mile wide section dropped about 12 feet during a 7.2 earthquake, and it did create a fairly local tsunami, but that had waves of almost close to 50 feet in height. And again, that was just when it dropped about 12 feet. It's like if it had fallen completely off and into the depths of the ocean, it would have created a much larger tsunami. And then, of course, another way that we can get tsunamis is when asteroids or other objects hit the Earth's oceans, which has happened historically. We'll get more into that when we talk about space hazards, but it's something else to think about when we talk about tsunamis. And it says here that a tsunami-generating impact occurs about once every 6,000 years, and so it's not super unlikely to get asteroid-generated tsunamis. And there are some areas where we know that big things have hit parts of the Earth that are, either next to the ocean or right in the middle of it. Of course, when an asteroid hits directly in the middle of the ocean, it doesn't leave a whole lot of evidence when we're looking at it hundreds of thousands of years later, other than you might find places where you could tell that there was a large tsunami because there's a certain, the shorelines get certain kinds of deposits from when there's tsunamis, but you don't necessarily get impact craters. But there are some, like Chesapeake Bay, which was about 35 million years ago, where about mega tsunami waves were generated. There was a new asteroid that we know of. It's supposed to be coming in 2029. People are mostly sure that it'll miss the Earth, but it's 320 meters wide. If it says if it punched through the Earth's atmosphere, it would devastate a region about the size of Texas if it hit land, or create a gigantic tsunami if it hit the ocean. But oh, it's on Friday the 13th. What could possibly go wrong? But anyway, more than likely that one's going to miss us. And in terms of tsunami hazards, some parts of the world are much more at risk than others. Japan, of course, has a lot of tsunamis. There's actually big risk here in the Pacific Northwest of the United States that sometimes is not necessarily recognized. Of course, Hawaii and a lot of the areas around what's called the Ring of Fire around the entire Pacific Ocean. But also some places you might not expect, like Pakistan or the Mediterranean here in Italy. This isn't showing up in red, but there was actually one of the larger tsunamis that killed a lot of people a couple hundred years ago was in Portugal when they had a tsunami off the coast there. So different areas are more susceptible than others. All right, so that is it for this module. And I'll put this whole PowerPoint up, but as you can see here, there are more slides below. It's a good idea to take a look at the review sheet to see what things that you might want to focus on or look through if you have any questions. And of course, always feel free to contact me as well. Okay, that's it for this module. Thank you.